Welcome to the Fork Join. I am one of the hosts, Oliver.
Hello, everyone. I'm Rachat, and today we have a great guest for you all to chat with. Harry, do you want to introduce yourself?
Yeah, totally. My name is Harry Goldstein. I am a PhD candidate at the University of Pennsylvania. I study programming languages and also some human-computer interaction. And my work is on property-based testing, which is, I guess we'll get into that in a moment, maybe. But yeah, that's who I am.
We usually start off with a couple of icebreaker questions, and I think, well, you mentioned PhD candidate, and people might not know the distinction, but we'll get to that. So my
Sure.
big sort of icebreaker questions for you are, what got you interested in computer science? If you remember your journey, and what made you pick your PhD and your thesis topic and all of these things, and then you can explain what a PhD candidate is and how they're different. Um, yeah, but
Sure.
go ahead, Ari. So.
So I started off, I started programming in high school and I really loved it. I thought it was a lot of fun, but I also really loved playing around with like electronics and things like that. So when I went to college, I started majoring in electrical engineering. And in that first semester, I took, a couple of EE courses and one computer science course because it was going to check off a requirement. And I immediately realized that computer science was just more fun for me. So I started going down that path and I planned on being a software developer. But then in, I think, sophomore year of undergrad, I took a class with Adrian Sampson, and he was teaching PL. And I was like, oh my gosh, this is so cool. So I asked him if we could do research, and we did some research. And there was a fun conversation at one point where he asked, do you think you'd want to do a PhD? And I said, maybe if I can get someone to pay for it at some point, if I can get a company to pay for it. And he said, they pay you in computer science for a PhD, right? And I said, no, I did not know that. Um, and that's kind of when the PhD route really became the thing. I had always had it in the back of my mind. I love learning. I love reading about cool technology. But when I realized that I could do the PhD and that like that was an option that was kind of immediately available for me, that's when I really went for it. Um,
Yeah, you highlighted this interesting fact that, like, I think once we all become PhD students, we forget that this is in fact a fact that, like, in the US, if you do something like computer science, not only is it fully paid, you get a stipend
yes.
in addition, and it's sort of normally you're not even paying for your master's. And in some countries, you end up paying for your master's and then your PhD is covered or something like that. But in the US, you get a combined master's PhD program and you're paid throughout the duration. Which really, when people learn about it, it really shifts the calculus sometimes.
Yeah.
And if you're US citizens, there are all sorts of nice programs where even if you're thinking of coming from industry back into academia and doing a PhD, the US government has this extremely amazing program. I think it's called CS for you or something. There's an NSF link for this that we can
Mm.
paste in the chat, but they'll basically give you a fellowship to come back to academia and sort of try out the PhD thing. So it's a really remarkable thing that is made possible. Well, I guess by the generosity of agencies like the NSF. But yeah.
Yeah. So I kept working with Adrian, and that was fantastic. We had a great time, and I ended up coming to Penn. I ended up here, and right now I work with Professor Benjamin Pierce. Uh, he's great, and he when I got there, I picked Penn because I felt like Benjamin and I sort of fit well from a research perspective. But the actual topics, we didn't really have one chosen. And he was doing a lot of testing at the time as an offshoot of some of the work on Deep Spec, which was a whole big grant from the NSF, and also specifically as part related to Leo Lampropoulos' thesis. So Leo Lampropoulos, professor at Maryland now, was a postdoc when I was starting. He was working on property-based testing. I got into it, and I sort of went back and forth on topics in the first couple of years, but property-based testing turned out to be the thing for me.
Yeah, you mentioned this moment when you took the programming languages class and you're like, this is really cool. I'm wondering if you can sort of highlight particular parts in the course or like particular lectures that really caught your imagination, because I know like PL courses are not a standard core curriculum topic at most schools. And so I had a very similar experience when I took my first PL course, or actually read my first PL book. And so I'm just curious what your experience was and what really hooked you into this work.
I think what I love about PL is the way it lets us be precise about abstraction. It lets us so like early on when we started learning language semantics, started learning I mean even just the untyped lambda calculus and sort of looking at the way we could formalize a thing that I had previously not thought about as formalizable. And the fact that the formality bought you something, like when we, I think we also looked at imp, and we looked at the way that you could do proofs about how an imp program would behave, that required you to be specific about what that program was doing.
So for the audience,
Um,
imp is like a folklore language. It's like a very simple imperative, or for many people normal programming language where you can like write, well, depends on your version of imp, but usually it's very simple. You can like write to variables and you have like some loops and conditionals and stuff. But like in this PL course, they were using this small language as a model for real programming languages and learning how to study
right.
programming languages, which we call PL. But yeah,
Yes.
uh,
Yes.
please continue, Harry.
Uh, yeah. Sorry. I'll try better to define things as I go.
No, it's okay.
Um.
That's what we're here for. So
Uh. So right, and then the fact that you can reason about these things, and then you can reason at higher levels once you've kind of built abstractions. I just think the way it all fits together is really beautiful, and the fact that it sort of ties into something incredibly practical, which programming kind of runs the things that we do every day. um I just really enjoyed the way that PL kind of tickles both the math side of my brain and the like, wait, this actually is useful for something side of my brain.
Yeah, that's sort of really cool, right? Like I think my memory of what got me hooked, it's actually very precise because I remember I was programming when I shouldn't have been. So I went to like math club at my undergrad university, UMass Amherst, and they were talking about this thing called functional programming, which I had not heard about. I programmed in C++ a little bit, and sort of I could write code, but I didn't know about this like other style of programming. And so they talked about it, and I was super excited. Um, and I was like excited to learn about it. And the club was over, so I went out, but it was raining outside, so I had to just stand outside the building waiting for the rain to stop because I hadn't gotten used to New England yet.
Mm,
And by that I mean always carry your umbrella no matter how sunny it is outside. You have to carry
yep.
your umbrella, right? And this person came up to me and they were from the math club. They were like, "Oh, you seem really interested. Why don't you go read this book? It's called The Structure and Interpretation of Computer Programs." It's this famous book from MIT on Scheme and Lisp.
Yep.
I started going through it, and I remember very clearly I was sitting in my economics class and I was writing writing code. I should have been doing it. And I came into the example where they teach you how a map function works. And the first time I used a map function where you could sort of pass in a function as an argument and then apply it inside, it just blew my mind, right? Like it's almost comical every time I tell the story, but it really was like an eye-opening moment. Like it was just like, wait, functions you can just like pass around and do all sorts of things. Like it's a whole new stack of abstraction that's open for you, right? And so that night I emailed half the department asking someone to teach me about functional programming and the lambda calculus. So that was my very vivid memory of like, like by understanding these abstractions and eventually understanding how to formalize them and make them very precise, programming languages really gives you this power to sort of build expressive tools that also have very strong guarantees.
Yep.
Um, Oliver, I don't know if you had a story like this that you wanted to share as well.
Yeah, I think I have a story shared by many people, which is that I love video games, and I was like trying to write my own video games. But the more I wrote, the more time I spent on writing my video game, the more time I found myself just like writing more and more complicated, weird Python abstractions to like write down my game states in a nice way. So I was basically, I didn't know it at the time, but building domain-specific languages. And when I figured out this is like a real thing that people do, and you can just build your languages, that was very exciting to me. And I started like looking into research in programming languages. I first tried like some research in some other areas, and it wasn't as interesting to me. But I sort of gravitated to like this idea of a language and what you can and can't do in a language as being very powerful.
Yeah, it's cool stuff. This is, I guess, a very specific question, but
Mm.
the question basically asks, since you were at Cornell, the audience member is curious about what kinds of PL related courses and research at Cornell really got you to the next step beyond just like, oh, this is like a spark of interest, right? Like I want to learn more about it, but what was your journey after that, right? Like, so I think this is
Yeah.
what the question is getting at, hopefully.
So the thing that really was the path between, oh, this is cool, and PhD was finding a professor who you can meet with every once in a while and do some research. Um, Getting in touch with the PhD students. I had some amazing PhD students there while I was an undergrad, and they were happy to talk to me and to sort of teach me about things and to accept me into the PLDG discussion group. So I think finding mentors was totally critical. Um, I think also in terms of kind of classes to take and stuff like that, take seminars. So the 4110, 6110, which are the two programming languages courses, were obviously great. But beyond that, like I took a seminar on cleaning algebras with Dexter Kozin, and a lot of it went over my head, but it was the best class I've ever taken. It was just so much fun because Dexter is so excited about that stuff, um and it was just like exciting to go to class and just have someone talking to you about like their favorite things. So
Yeah,
those would be my
Yeah,
recommendations.
that's cool. Yeah, find passionate people and good mentors is the takeaway, I'd say.
Yeah.
yeah. I think Cornell. I'm biased because I'm I'm from Cornell too, and so you have access to all of these great programming languages class. But I do want to say that, especially in the U.S., a lot of schools, I think like CMU and I think UPenn have now started undergrad research exchange programs where you can apply to be a research assistant over the summer and be paid by the university and work on one of these topics. So even if you don't necessarily have these opportunities at your school, I think if you're interested in doing the kinds of work that Harry is describing, that's sort of those are programs that you should look into and sort of apply to. And I think like that could be a great way to start building that mentorship network. This
Yeah.
this
I'll
yeah.
make a small plug for Penn's REPL program, which is our RU in PL program. The first summer of it is, wrapping up this month. But for y'all out there, especially with from marginalized backgrounds, please do apply to that. It'll happen next summer and the summer after at least. And it's a ton of fun.
Cool.
Speed
Well,
should
that was a great, yeah, intro. I'm very interested though in what is this property-based testing thing and how would it benefit me in particular? Uh,
Of course,
I'm
yeah.
very interested in this. Yes.
Okay, so property-based testing is a form of testing that is kind of that is very has the ethos of programming languages, right? So rather than writing down normal kind of example-based unit tests where you say like, okay, here's an input and here's what the output should be, you instead write some property, some kind of mathematical statement about what a program is supposed to do. And in particular, you write one that is executable in some way. So, for example, that is sorry, that's not the one I was talking about. I will send you the REPL link.
oh, okay.
That right. So you're writing down an executable specification. So, for example, maybe you write that for a sorting function, the output of the sorting function should be ordered, right? This is a thing that you can think of this property as a kind of checker of something you want to be true of your sorting function. If you give it some list as an input and you check the property, you can check that for that particular list, sorting it gives you something that's ordered. And if you check it for lots and lots of inputs, you can get more and more confident that everything you put into the sorting function will give you out something that's ordered. And this is the core of property-based testing is you write down an executable specification, and then you test it with lots and lots of examples. And concretely, those examples are usually generated randomly. Sometimes they can come from other places, and we can talk about that if y'all want to. But for the majority of the PBT literature, we're talking about randomly generated inputs. So you can the real power here is that now you don't have to think in terms of these individual examples. You don't have to think about, when you're writing unit tests, sometimes it can be really a real struggle to think about which examples do you want to test and how many unit tests do you want to write and all that kind of stuff.
And it takes
This
time to write a
really,
bunch of examples,
and
right?
it
And
and
do
it
them
takes a
by
bunch of
hand and
time.
like
Yeah.
figure out what the answer should be.
Yeah. And so property-based testing sort of takes a step back and says like, well, what do we actually want to be true? And then automatically with a random data generator checks that that's true.
So is there this implicit assumption that it's easier to check that the output is correct than to like compute that answer in the first place? Or is it more like maybe even if it's very hard to check that it's correct, writing two complicated programs, not just one, and checking them against each other, like your tester and your main program, will still give you like something. Like you may have to
Um,
spend twice as much effort, but you'll still get to check two programs against each other, which will give you some more confidence.
I think both. I think depending on the kind of property-based testing that you're doing. So the example you'll see most, the thing you'll see most in the literature is the kind where checking the output is easier.
I see.
This is true of the sorting function. This is true of in my papers, I usually use an example with binary search trees because it's just kind of the right level of complexity for examples in a paper. But the real world, and I want to get back to this in a bit, but I've been talking to developers who use property-based testing in the real world, and their use of property-based testing tends to be more like the second thing you said,
I see. They build a
where
complicated checker.
you sort of build a checker that is sort of a simplified version of the program that you've written. Maybe it's less optimized, or it's different in some way where it's easier to check that that second program you've written is what you
Or
mean.
even just slower, like fast code is harder to write than
Exactly.
a slow, naive version. So maybe your checker
Yeah.
is like the slow version.
Yeah.
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 I, I want to, I think you've hit a very deep point about what testing is, and I want to philosophize about this for a moment, right?
Mm.
So if we think about the normal software development process, you write some code and then you write some tests, right? And in some ways, when you start out, you think of those tests as exercising your program, right? We have all of these metrics like code coverage, branches coverage, and stuff like that, that really just tell you that, hey, this code executed once. And oftentimes people use that metric as a metric for the reliability of the code, right? The fact that a particular branch was executed means that, okay, at least the code has been run. At least the code has not, never been run by your test suite and is sort of going to get hit by a weird bad case when the user tries to run it. But when we think about property-based testing, it seems one thing that you have to understand is testing is about really specification, right? And so there's this like higher level bit that you have to think about, which is you write your program and you have an internal specification of what the program does. You have like a document that tells you what the program is supposed to do, and you sort of have the architecture of the software that you're building. But in some ways, what you're getting at is defining the specification. So I'm curious about this philosophical difference in how you specify the correctness of your programs. Instead of just trying to exercise the code, now you're literally defining functions that specify its behavior. And then, that is the basis of what property-based testing can utilize to generate a lot of outputs. But I think specifications are the thing we should talk about first. And, can't be a CS podcast without specification talk, at least.
Yeah. I mean, I think this is both the in some ways the best and the worst part of property-based testing from a user's perspective, because it's hard sometimes to specify what your code should do. You write down a function, and sometimes you think like, well, it does what it does. That's but at the same time, when you're sort of made to do that, and you're made to think hard about what the code is supposed to do, that in and of itself can help you to understand what you've written and understand what's supposed to be happening. And then property-based testing lets you check it without having to prove it like many folks do, which is also great, but it's easier to check it. In terms of the kind of philosophy of how to specify your code, I have unfortunately this is a very broad topic. I have some advice. So John Hughes has a paper called How to Specify It. It's also a talk on YouTube if you prefer audio media. And it's a lovely little look into the different ways one can go about writing specifications for code. I think I think there's lots of examples of kinds of properties people use. So there's all the kinds of things that John lays out in that talk. There's also like differential or model-based testing, which is the thing I was alluding to a little while back, where you actually have two versions of code that should do the same thing, and you're just checking that they
Right.
agree. That's a different kind of specification. That's like a model-based specification where it's not a mathematical formula. It's a model of the code that you want.
I think
But
I
but
found the property-based torture a very funny quip because, that's what Harry was saying he wanted to do. Like, property-based testing, Harry says, is great because it forces you, the human, to think harder and be
yeah,
tortured by your specification. And, like, that human process, even if you have to write some other code that also might not be correct, the, like, process of trying to write that code may improve your program as well. So
yeah,
I found
for
that
sure.
like a very interesting perspective on testing. Um, I found that in the past, like writing tests or even trying to like verify your code in a more formal way can really improve the code itself. Yeah.
Absolutely. Yeah.
Sorry,
Yeah,
I
so
didn't
there
mean to interrupt your line of thought though.
I think the thing I was going to simply sum up is that uh, I don't have a kind of all-encompassing philosophy on specification because it's hard and incredibly varied.
And you
Um,
have many different kinds, right?
yeah, but I think that's one way that property-based testing connects into the rest of what's going on in programming languages right now is through the specifications, because a lot of the other stuff is verification, right? You also need specifications for that. And projects like QuickCheck in Calc let you check do property-based testing on the specifications you're about to prove, which can be really useful.
Yeah, so I guess this is a great segue. I don't know if Ratchet was about to say something
yeah
into
I,
the other big benefit of having a spec, which is that now you can like randomly test it and that sorts of things. Ratchet.
yeah no I think this specification is like, I think in some ways a deep part of the kind of research a lot of programming languages researchers do. And it's sort of like, if you think about the social process of designing systems, right? There's the first part, which is you brainstorm and you try to understand your problem space, and you sort of, you're free to sort of explore as much as you want and come up with various design points and sort of justify what choices you're making. But once you're done with that, you have to do specification. You have to specify in some way what your software or what your system is trying to do. And that's really, it's not just about computers, or in some ways the fact that computers can use specification is besides the point, right? It's like it's for us humans who struggle to understand big complex systems in sort of finer levels of detail. So we need to abstract. And so specification is this like other side of abstraction. The fact that a very complex assembly-based implementation of sorting implements the very simple bubble sort loop that we wrote here is useful to us because we can reason about that bubble sort. We can't expect everyone in our teams to understand what that low-level assembly code is doing. So I think like, central to a lot of the ideas that we think about, especially as programming languages researchers, like type systems and verification and property-based testing and fuzzing. Um, Specification is sort of at the heart of it. So I just wanted to say that it's just like it's a very important thing. And like even if you don't do research, right, like you will be specifying the behavior of your software. The only question is how formal you want to be. Do you want to write it in docs? Do you want to put it in sort of little functions that implement your behavior but are slow? Or you want to like go full blown sort of verification route, which again we'll ask Harry about later in the chat.
Yeah, and
Um,
all of these have trade-offs. We're not saying one's better than the other. We're not saying like if you're not verifying your code, you're a bad programmer. It's like everything, like this whole spectrum of testing to verification. There's lots of trade-offs here. Like if you do property-based testing, you have to write some sort of more complicated spec that's like checkable against random inputs. But if you
Yeah.
just write hand tests, you write individual inputs and outputs, there's no code, just data or something like that. So like there's big trade-offs here for sure.
Yeah.
right. I think we have a interesting question that will force us to delve a little deeper into your work in PBT. So the question says, you mentioned that in PBT, a lot of tests are randomly generated. Is there a way to formalize this into a probabilistic guarantee of correctness with some probable upper bound for incorrectness probability? Okay, that's a very deep technical question, but let's see. Let's try to break it down a little bit
I mean,
for
I
the.
think it's a great question, right?
But
The
you got to
the
explain the question to us first, for us peasants. I think we need to understand what the question is really getting at.
Yeah,
Yeah, good idea.
yeah. So when you do property-based testing, right? Let's say you generate 10,000 inputs for your program, and you want to know like, well, the distribution that those inputs are drawn from, and it feels like you could say like, maybe now that I know I have 10,000 inputs drawn from this distribution and I've run them all through and none of them found a bug,
Mm,
maybe I can say something about the probability that there is still a bug in that program. Um, I think it turns out that you kind of can't. But there are things you can do, and I'll get to that. But let me first try to motivate why I think you can't. And the reason is because there's actually two distributions involved. There's the known one of the distribution of inputs, but what you don't know and can't in principle know is the distribution of bugs in the code, is the likelihood that any particular part of your code has a bug in it. If you knew that, you would actually just go to the places that are most likely to have a bug and squash the bug.
And that's a great way of phrasing it, because that's exactly the art that you're trying to like promote here, is the art of specifying a distribution you think will hit bugs, right?
Yes. Yes. You're doing your best to craft an input distribution that you think, based on your guesses about the bug distribution, could trigger bugs. But the problem is, without knowing what the bug distribution is, you can't really come up with the probability that there are no bugs.
So
Now, here's
yeah.
things you can do, because I think that this is that sounds kind of sad, but there are alternatives. So one of my favorite ways of kind of getting at uh, some kind of idea of like how well has my testing done, is mutation testing. So in mutation testing, you go into the code and you inject bugs. You make it wrong on purpose. And then you run your property-based testing. And the goal is to make sure that your property-based testing suite actually catches all the bugs that you know are there because you put them there. This is nowhere near perfect for making sure there are no bugs, but it is a pretty good proxy, especially if you're doing a good job at injecting the bugs.
Yeah, so mutation testing is a whole extra thing where like there's another distribution, which is you pick a distribution of bugs. And now you're
Yes.
saying like, okay, I don't know how to find the actual bug distribution, but what if I pick a bug distribution where I inject bugs?
Yeah.
And there's a whole like problem here, which is like, how do you know you inserted a bug? Like, how do you know your bug distribution are actually bugs? Like this, there's like a big rabbit hole here, but I like mutation testing is very powerful, and I agree it's a very great idea.
Yeah.
Yeah.
The other option is to look at the some feedback from your testing. So code coverage in various forms, like line coverage and branch coverage. Um, I did some work a while back with combinatorial coverage. So this is actually not a measure of coverage, output coverage. It's a measure of input coverage, but it tells you, sort of to some degree, how well the inputs that you generated cover the total space of inputs. Um, this doesn't really give you the thing you want, which is anything about the code under test, but it does give you a good signal that you're missing something if the combinatorial coverage is too low, because it means that there's some part of the input space that you're skipping over, that you're missing. But yeah, I think those are the main techniques that I tend to pay attention to. Is there's things you can do to measure how good your inputs are, and there's things you can do to measure how well you're exercising the code, but you can't really get to the probability that you'd like.
So the great answer, and I think it's like it sort of gets to the heart of the specification problem, right? Like you have to figure out what to specify. And so I'm going to ask a very dumb sounding question, but I think there's something there, which is, what is a bug, right? I think it's important to specify what a bug is before we talk about catching them. So let's talk about bugs and various ways to catch them, right? Oh, there's a book title here somewhere. Uh,
Yeah. I mean, in a sense, a bug is I think a bug is the thing you'd catch if your specification was the thing you meant, and your code didn't satisfy it. The problem is you can write a specification that isn't what you meant, and you can also fail to catch deviations from your specifications. But fundamentally, I think a bug has to be in that gap between the true specification you meant and the behavior of the code.
Right. So there's a related technique that maybe some of the audience members are also familiar with called fuzzing, right? And fuzzing, in some ways, when you think about fuzzing, where the idea is you take your binary, you compile your program maybe, and you take the binary and you just attack it with as many inputs as possible and see if it crashes. Well, you're not doing any specification here. And so what's going on there? Is it different from what PBT is? Like, what is the relationship between fuzzing and PBT? And does it get to this question of what a bug is?
Yeah. So first, I'm going to disagree. You do have a specification.
Right.
Your specification is the program doesn't crash. Or depending on exactly how your fuzzer works, also that might include certain memory vulnerabilities.
That's right.
And that is an important specification, right? The specification that fuzzers generally deal with is critical. I think the main difference between fuzzing and property-based testing is that fuzzing is focused on integration testing of large systems for security properties that like crashes and memory safety issues, that if your program were wrong in that way could lead to vulnerabilities, security vulnerabilities. That's really important, and it's important that we have really good tools for that. And you wouldn't do integration testing without unit testing. And so I think that's where property-based testing comes in, and that's where property-based testing is different. It's focused on specifications at a more granular level, because at the integration testing level, it's hard to have a specification more specific than my code doesn't crash. But at the unit level, you have abstractions, and you have abstraction boundaries, and you have more particular things that need to apply at those boundaries. And property-based testing lets you talk about the specifications that are that granular and gives you the tools you need, because you need slightly different tools to test at that level. And I think there was a question in chat about generation, which when we're done with this conversation, I think we can segue
Yeah, I think
into.
that's a great segue into your research. I'm very excited to hear about, like, how should you write this probability distribution, and maybe you can write it in a convenient way so that you can get even more tools automatically from them.
Yeah. So right. So I want to make sure I've adequately addressed the fuzzing question.
Exactly.
Are we happy with that?
Yeah, I think one thing that I'm taking away from this, and this makes a lot of sense, which is that much like how there is a spectrum between sort of the formalism you use or the not formalism you use to specify the behavior of your design, there's also levels of how much you specify, right? Do you specify, do you want to go to the level where you're saying floating point addition is correct? Is that a part of your specification? Can you detect it, right? Like most machines, if there's a bug in your floating point implementation, how do you even check it, right? And so there's a question of like, what is your base of trust, which I think people in sort of verification community call the trusted computing base, right? What is the basis of your trust? And then when you have that, what is the specification that you want to enforce upon your program? And so like you can imagine that if you're, let's say, building a microservice, you could say the latency of this microservice or the tail latency is for like 5 nines or something, is important to me. And that should be a part of my spec. And if I ever violate it, that should be considered a hard failure or a bug in my system, even though it's very hard to attribute any one single line as a problem in that case, right? Like I think this is the high level point I want to just say here, which is that oftentimes when we think about bugs, we're like, oh, this line is wrong, or these 5 lines are wrong. But sometimes it could be like a system level integration property that is violated that we care about, like latency. I see we have a lot of questions in the chat. So
we do.
I'm going to try to collect them while Harry, you talk about the next topic. And then once you're done with the introduction, I'm going to sort of pose all of those questions in like a big chat message, if that sounds good.
Cool. Great. Yeah. So I think I was saying that property-based testing needs different tools than fuzzing. And this is obviously a spectrum, but the problem that comes up in property-based testing that comes up to a smaller degree in fuzzing is that when you have really complex properties of a system that you're trying to test, those properties have preconditions, right? Those properties require the input to be of a certain form before the property applies at all.
Yes.
So a good example of this is in the binary search tree example that I always use. Let's say you're inserting a thing into a tree. In order, you want that insertion to result in a valid tree. So you have some notion of validity, and you say that, okay, well, when I put something into the tree I get out had better be valid. But actually, in order to check that, you need to start with a valid tree. The actual property says, if I have a valid tree and I insert something into it, then the output tree is valid. And the difficulty here is that generating randomly a bunch of valid trees is actually not that easy. And in fact, depending on what your property's preconditions are, sometimes this is not computable at all. Sometimes it's impossible in general to automatically find the valid things. There's a question that this happens in fuzzing too. Absolutely, it does. However, when you're at the boundary of a program, this is anecdotal, but when you're at the boundary of the program, the constraints on the inputs tend to be not quite as strong. The examples we see in property-based testing just happen for I guess because you're kind of lower down into the program, happen to be more complex and harder to satisfy. And so fuzzers do a lot of work to make sure their inputs satisfy the preconditions that the programs have as well. But those same tools, when you get to the level of the kinds of preconditions that I care about when I do my research, they don't tend to work well enough. And so what we do in property-based testing instead is we write generators. We write programs that are designed specifically to only output things that are valid, to only output things that satisfy the property's precondition. And those generator programs come in a bunch of forms. And one of the things that I do in my research is I design domain-specific languages for this generation that help you to do your job in producing valid things that adequately exercise the property.
That's great because I was about to ask you, wow, to do this PBT thing, property-based testing, I have to write a generator by hand, I have to write the spec by hand. It's starting to sound harder to test my program than a lot of other things than to write manual tests.
Yes.
But maybe if we have the right tooling, it becomes a lot more feasible. And you're saying you have domain-specific languages, little ways to write down your tests that reduce the human burden a lot.
Yes. So the quintessential thing here is the quick check framework in Haskell, which popularized property-based testing, provides a monadic domain-specific language. So it's if you know Haskell, that makes sense to you, and if you don't know Haskell, I'm not getting into monads here. But the idea is it's just a language that gives you easy tools for taking random generators of small things and putting them together to make random generators of larger structures. And to allow yourself the flexibility to do things like defining generators for binary search trees or well-typed programs or whatever you'd like to generate. My research has been sort of building on those the domain-specific language that exists in Haskell. I it's interesting. I have not quite yet succeeded in making it significantly easier for the user to write these things. At least not much easier than QuickCheck's domain-specific language already makes it. The languages that I've built give you more features. They help you kind of elsewhere in the testing process by giving the generator kind of more that it can do. And I'll quickly plug my upcoming ICFP paper, which is called Reflecting on Random Generation, where you can use your generator to help you with test case shrinking, which is a really important part of property-based testing that lets you find the smallest example that triggers a particular bug. And check out the paper. I like it. I think it's a neat idea. But we can get into debugging and shrinking at some point if y'all would like to. But on the horizon for me and the kind of next steps is making these things easier to use. And not just easier to use like kind of in the abstract, but easier to use by like evaluating how users interact with these things and making it easier for actual people out there in the world who would like to use these tools.
Yeah, this is sort of okay, two things, I guess. Just to check my understanding. What you're saying is, okay, so we've set up the PBT problem, which is that you have some program, you've written your program down and you want to test it. Right. And so you need some mechanism to specify its behavior. Or actually, no, you want to specify its valid input space. And what you have done, Harry, is, and building on other people's work also, is define a language for specifying valid input spaces through composition and abstraction and all the other things we like about languages, right?
Yep.
And so what this hypothetically means is that instead of writing low-level generators for your input spaces, you can use the high-level constructs your language exposes and make someone who's doing PBT much more productive. That's the hope, right?
That's
and
the
so,
hope.
right. And so before we get into that, I think it would be useful to think or just explain what the workflow of someone who's doing PBT looks like, right? And by that I mean, like, okay, we can think about the edit compile debug loop of a standard program, but what is the edit compile loop of a PBT generator, right? And so just very pragmatically, if you are like, there are YouTube videos of like a day in the life of a baker or something. What does the day in the life of a PBT engineer look like?
Yeah. So I'm going to be slightly vague about some of this because there's stuff under submission right now. But from what I've seen, it looks like the same workflow that people are doing with example-based unit tests, where you're writing your code and you're writing your tests sort of back and forth, because you did a little thing and you're like, well, does that work? And so you write some tests down. And you get to a point where early on in the process you are you're not writing your own generators because people are trying to make forward progress. And so what they're doing is they're using tools that exist in the world to automatically derive a generator. Those generators, critically, don't always satisfy the preconditions that your properties have. And so you can end up in cases where they're not doing very much. They're generating a bunch of stuff, but that stuff is getting dropped on the floor because your precondition isn't being satisfied enough.
So they just filter
But
them. Like they generate a
you
bunch of
just filter them.
inputs and
Yeah,
you're like the ones that aren't valid, just throw them away.
just throw them away.
But what if that's
Um,
really improbable to get a valid input? Is that the problem you're saying?
yes,
Right.
yes, and so there's for some preconditions. So let's say your precondition is not equal to zero. That's easy, right? Every once in a while, we'll generate zero and we'll drop it on the floor, but we don't really care. But if your precondition is a binary search tree,
Uh-oh.
it turns out that's very unlikely. And worse, when it is satisfied, it's probably satisfied by a very small tree, right? It's probably satisfied by the empty tree, because that
Right.
is a valid binary search tree, but it's not a very interesting one. And so the way this workflow sort of plays out is people reach for the automatic generators because they're there, and then at some point, maybe if they're lucky, they realize, oh wait, maybe this particular generator isn't doing anything here, because they realize that their property's passing, but it's just dropping a lot of things on the floor, and then they go back and they refine the generator so that they can make sure that they're adequately testing the property. Um, One thing that I'm finding, which I want to pursue further, is that I think existing tools don't quite give you as much information as they should, so that you can know when you're in that situation, so that you can know when you're in the situation that um, something has gone wrong, your generator isn't doing interesting things. Every framework has a kind of different approach to this. Some are better than others. But kind of across the board, I think giving users a little bit more visibility into when their generator might not be doing its job is, I think, a really important next step for property-based testing tools.
Yeah, just to add to that, I think like getting those statistics and information back from such a complex tool that does property-based testing is really important. I know that engineers at Google frequently use mutation testing, which we've uh, touched on a little bit before.
Yes.
But their mutation testing framework, like the internal Google one, is much more advanced than most because it gives you a lot more rich information about what it actually did and like UI for how to deal with the mutants and how to resolve them, or how to give feedback back to the tool, like this mutant wasn't very useful. Don't generate things like this. I think those interactive human in the loop sort of processes are extremely valuable in the real world when you're developing real software, like a property-based testing technique where you can like dynamically interact with the tool and tell it which things were useful and which things were not, skew the distribution or avoid certain paths. I think that's very promising in my mind.
Yep. Totally agree.
Yeah. I have like given the amount of time you might end up spending building one of these test engines, which could be valuable in the long term, I guess one thing I want to chat about is sort of the social norms around building software and how that affects the amount of investment we can give to particular technologies like PBD, right? Like I think fuzzing and sort of static analyses and type systems to a lesser extent benefit from the fact that they're sort of, well, the first two are almost always fully automatic. And so you take it, put it in the CI, and they just run. Type systems require some overhead depending on your language. And we've seen the amount of pushback we get from people, maybe not so in this decade, but in the previous decade, there was just like a lot of skepticism that type systems are necessarily useful for the kinds of software building. So PBT also occupies this space where, if you're working on a test harness or PBT harness, you have to justify to your manager the week you're going to spend on it, or like 2 days you're going to spend on it. And so it's a funky question, but like, have you thought about how people can quantify the benefits of building systems like this, right? Because it's not like I added feature X. It's like I enabled testing. What does that give me as a
Yeah, you
corporate?
could spend like weeks writing your specifications for different bits of your code base, and it was like a lot of hard work. How do you like justify this?
Yeah. So I think uh, justification and the kind of social process of property-based testing is tricky. I think there are cases where it's obvious that it's worth it. So these are cases where you know you don't have the budget to prove this thing correct, but you do know what you want it to do, right? You do have a specification in mind. And so it's pretty clearly worth the effort to put in the effort to make a good generator, which is still way less effort than to prove the thing, so that you can check that this thing is correct. There are also cases where generators are pretty easy. So, for example, the model-based kinds of properties tend to have lower burdens on the generators. And there's also ways to do it where you can kind of rely on the system itself to build a valid input for you. So, for example, rather than generate a binary search tree, you instead call insert a bunch of times, and that will automatically build a binary search tree. Another good example of one of these areas where it's kind of easier to get valid things is round trip properties, where you sort of maybe you parse a thing and then you pretty print it, and you pretty print a thing and then you parse it, and you make sure that you get the same thing back. There's lots of examples of kind of easier properties whose preconditions tend to be on the easier side, where property-based testing is like a kind of easier win.
Yeah, I
I
like
think
this
there's
round. Sorry, I like the
yeah,
round trip example. It's one that I use in my work like this week because the specification is already sitting in your code base. Like you
yeah.
know that two functions are inverses of each other, or you should get the same thing going through a bunch of parser and desugar or deserialize steps. Um, so if you already have that property, that's very convenient and it's a clear win.
Yep.
Sorry, I
Yep.
interrupted you.
And then I think there are cases where once you've gone to the trouble of doing the specification, you actually do want to prove the thing, right? Like there's the cases where property-based testing is too much effort. And for those, you either have to decide that it's not worth the kind of extra confidence that it would give you, or you decide, actually, I do want to put in the work. But then there's the other side where you're like, well, actually, I want a guarantee. I want this thing proved correct. And in those cases, property-based testing is actually still really useful. And in those cases, in particular, if you're working in Calc, Leo Lampropoulos is continuing to sort of push the envelope there with making the process of testing a specification you are about to prove more and more automatic in a way that is hard to do if you're not already in a language like Calc. So the specifics there are complicated. I'll refer you to a paper called Computing Correctly with Inductive Relations, and the more recent PLDI work called Merging Inductives. And that is if you're the kind of person who actually wants the guarantees of proof, I still recommend you put in you do the little bit extra to property-based test it first, because it's really hard to prove something that isn't true, but it's really easy to test the thing that is false.
Cool. I think, yeah, we have a couple of audience questions, and maybe we should get to them now.
Yeah, it's a good
Uh,
idea.
so I think that there's like a theme in a couple of these, which is, okay, one approach to doing PPT is handwriting these generators. But the other approach is using some sort of sampling defined broadly. And it could be sampling over the outputs generated by LLMs, learned outputs possibly generated by LLMs, or doing something like MCMC, which is Markov chain Monte Carlo methods, to sort of try to sample random inputs for your programs. I think the audience member and I am also curious. Have you sort of thought about the impact of things like LLMs on property-based testing, both as a user of LLMs and as a tool that needs to exist in the presence of LLMs?
So
Yeah,
LLMs are large language models. They mean like machine learning, AI, all this
the
fancy
thing
stuff.
that backs ChatGPT.
Yeah,
ChatGPT.
it's the ChatGPT thing. That's right.
Yeah, it's the ChatGPT. Yeah, so I have lots of thoughts here. I think when we think about using LLMs to generate the inputs that we're uh, testing with, I'm not convinced yet. So there's some work on this. There's a tool called Codemosa uh, that uses LLMs to kind of get a fuzzer out of corners that it gets stuck in, which is really cool. I really like that. But I think that in a lot of cases, and this is a I think Caroline Lemieux, one of the authors on that paper, once said to me that, like, well, you do have to be careful because LLMs give you what you're expecting. And so property-based testing wants to find things that you're not expecting, at least to some extent. So there's like a lot of there's some back and forth that has to happen there. Um, I like the tools we have for generation, and I kind of want to keep pushing on those. But that's kind of where I feel about that. However, there's two other things I have to say about LLMs. First, I think they could be very useful in the defining specifications part of the process. So helping the user to take an informal specification and make it more formal, helping the user to sort of think through what their specifications might be based on other things that they have available. There's some work that sort of tries to guess what is more unit testing-y, but sort of tries to guess what your specification is based on your unit tests and things like that. I think there could be something really good in that space of like using LLMs as an aid in the specification process. I haven't really been diving into that at this point, but I think people are broadly thinking about it. And the
Actually,
other
just
thing is, oh, go ahead. Sorry.
oh, I just had an idea, which is that you said LLMs or data from the real world give you what you expect. What if we use those to motivate giving us what we don't expect? So, like, can we feed this data or LLMs into something that, like, filters out that input search space and allows our property-based testing to give us weird or inputs from hell, as the paper goes?
Yes.
Yeah.
Yes. Yeah. So Inputs from Hell is a very cool paper. And actually I reference it and kind of re-implement part of it in reflecting on random generation, the ICFP paper that's coming up. I think I played around with it. I haven't yet been convinced that, like, when you've got really complex preconditions, that Inputs from Hell thing does exactly what you want it to do. But it could be that I just haven't found the right way to do it yet. But yeah, I do think like certainly the information that it's giving you what you expect is useful because you can potentially take the complement of it in some way.
Right, right.
Um,
But that
yeah,
process is like not clear. It's a little bit hard to
yeah,
take the complement of a data set, right?
it's a little blurry.
Yeah,
Yeah.
yeah, for sure.
Um, the other thing with LLMs, and this is, I think, the thing I'm most excited about, is that people are using them to generate code. And that code might be incorrect. And people are not that good at reading code sometimes. And so maybe they're not very good at knowing that code's incorrect. But I still do use Copilot. I think it's a cool tool. It's a useful thing for generating code. And so the question is, how do we have confidence in our software when we're not writing it? And
Hmm.
in the same way that when your collaborator gives you code to review, you make sure they have tests because you don't trust yourself to see all of the bugs that they might have put in, right? If you're going to generate a whole function with Copilot, you better test it. You'd better make sure it does what you expect. And I think property-based testing gives you some really good tools for that. Sure, unit testing, sort of traditional example-based unit testing does too, but the advantage of property-based testing is that it's very thorough and forces you to think about what you actually wanted Copilot to give you in the first place, not just on a few examples, but more generally what behavior you expected the function to have.
Yeah.
And people have shown that you can use the feedback mechanism from tests to guide the process of generating code as well.
Yes.
Uh, you can sort of imagine a harmonious version of this where the only thing you do is you write perhaps a PBT like a generator, and that's your spec. That's your input specification to ChatGPT. It's currently not natural language, but it's not clear if natural language is the right sort of input language for generating code. It's certainly very convenient. So maybe natural language plus sort of a PPT that the system can run and evaluate against could be good. All are you saying?
Yeah, I was gonna say, in addition to like sort of all the other benefits we've been talking about and having a specification, there are some cases in the real world where it's impossible to write a unit test by hand. Like the data is just too big to write down by hand or too
Mm.
complicated. And so you're forced to sort of specify it. So I think that many people sort of throw their hands up in the air and give up once they can't write a unit test by hand and they test in production. But like you can like generate these
Yeah,
inputs, and so that's another benefit of property-based testing. Uh, yeah.
absolutely.
Sweet. One other question that I think will drive us towards this term you mentioned, shrinking. The question was basically, PPT is great. You generate a bunch of programs and you sort of fire them off randomly. You maybe even do it in sort of pre-commit, CI testing. But at some point, when you commit your code, you want to perhaps freeze your tests and have a regression suite, right? And so here's a question, which is, given this PPT model, let's imagine like tomorrow everyone is only using PPT.
Yeah.
First, is it valuable to have regression test suites still or no? And two, if it is valuable, how do we generate useful, human readable tests for people to commit and sort of have as a long-term, institutional or code-based knowledge for what the program is supposed to do?
Yeah. So, first of all, I want to say I don't think we should be in a world where people are only doing property-based testing. I think that property-based testing is great for certain things and less good for other things. And even for the things it's good at, it's good to write down a couple of examples yourself. I'm not a purist about this by any means. Um, and that means that yes, I think we should have explicit regression tests written down. Um, Hypothesis, the Python framework for property-based testing, does a really cool thing here, which is that every time a property fails, it saves that example into an example database off to the side, and every time it runs that property, it runs that example again. And you can commit that example database into your CI, into your repository, and that when you run CI, it's going to run that as a regression test as well. When it comes to sort of freezing tests, people will just freeze a seed for their property-based testing and do it that way. I kind of like the idea of CI continuing to run randomly. It does mean occasionally you'll get an error in CI that wasn't an error locally, but like you've got an error in your code and you'd kind of like to know about it. But that's
Yeah, it's
that's sort of people have different opinions on that. But when it comes to regression testing, I think the hypothesis approach is a good one. I could also see pulling those out into more traditional unit tests and making, trying to make them more readable and understandable. I think it depends on the failure, right? Sometimes you do want that regression test front and center as a kind of warning. Other times, you just want to make sure that we keep seeing that again just in case.
Right.
But yeah, I think there are ideas out there around for tools to kind of take a failure and turn it into a regression test in your code. And I think that's a good idea if you decide that that's the route you want to go.
Yeah, this also leads to again an interesting social processes question, which I guess is what I keep thinking about over and over, which is somehow, so if you think about a standard test suite, right? Like if you're thinking of a standard test suite for any company or like at Google scale or something, a nice property of test suites is that they are a finite, well-known commitment of resources or compute resources that give you back some, trust in your code base. With random approaches like fuzzing potentially or PBT or any other generative approach, it's not clear how much you should run your harness, and there are papers from UMD and other groups that show that like if you run things longer, you can effectively recreate abilities of differently proposed systems and stuff like that.
Yeah.
I'm being big here because I don't want to get into that rabbit hole, but essentially there's a question of like how should you decide how to commit resources, right? And I think it's getting back to this original question of like incorrectness probability. How do you build a trust in your system, and how should you allocate resources to build that trust?
Yeah.
That question makes sense.
Yeah, it makes a lot of sense. I think because it's hard to quantify the probability that you found all the bugs. I think it's not knowable in general, right? How long you should run your properties for. I think using other measurements as proxies, like how many newtons you squash or how well your code coverage does, is a good place to start. But I would like to do more research on exactly how, in general cases, how long people are running property-based tests for. Early results are saying that they tend to want to run them for a pretty short amount of time. They tend to really time box it. For fuzzing, they're willing to let it go longer. They're willing to run fuzzing for days and days. But since property-based testing is part of the unit testing discipline, you want it to run with your other unit tests real fast. And so I think that that is a challenge that property-based testing will continue to face, and that people who write PBT tools need to think about. But I also think that the easiest answer to the question for a start is to just decide how long you have to run the properties for, and then run them for that long. And this is why it baffles me that almost every framework out there has a number of tests, not an amount of time, as the cutoff for testing. It seems to me that you should be able to time out the property-based tests. That like what you actually want is I have half a second, and however many inputs you can squeeze in half a second, that's what I want you to do. And so that's, I think, in the absence of better data, that's the recommendation I have is come up with a budget and spend the budget, because you do get better effects the longer you run your properties for. But in the real world, we don't always have infinite time to do that in.
There's another benefit to specifying a time, which is that often we consider performance a bug. And if you're not able to run the same number of tests under the time as you used to be able to, it might be a problem. And these
That's
are
a
like great things to keep an eye on, for sure.
Yeah.
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 I had essentially the same comment, but maybe on a different angle, which is like it harnesses the scaling effect of computing itself, right? It's like if I say I want my test to run for a minute, well, a couple of years from now, if your code is faster or your underlying machines are faster, that means more tests run.
Yep.
And you don't have to justify sort of any resources, any sort of resource allocation changing over time to your manager or anyone. You can just be like, I want a minute. Every day when these tests run, I am taking a minute out of your time. Is that acceptable? And if they agree to that today, 5 years from now or 2 years from now, like that is still acceptable probably. And it's a quantified cost and amount of computer resources, and you can get more trust over time potentially,
Yep.
if your system's improving. Um, but I like Oliver's comment here because I really wanted to get to more of these amorphous properties. I don't know, like sort of properties that come from system integration as opposed to just sort of low level, functional correctness kind of properties. And I'm curious if you have thoughts on how to encode things like performance or latency or throughput or reliability as random properties, not even just the world of PPTs, but thinking more broadly, how should we what is the right way to test these properties, right? I guess that's my question really. And do you have thoughts on this?
I mean, I think property-based testing gives you tools that I think should be helpful for testing those kinds of properties, right? You can carefully control the input distribution, so you know you're not getting inputs that are outliers in terms of size. I think that would help to kind of uh, give you a little bit more control when you're trying to test performance properties like that. And I think that obviously, if your code only runs on valid inputs, then you need a property-based testing like generator to produce those valid inputs. But I don't have. I'm sure something is out there that either something's out here that does this, or this is a thing that someone should do. Is kind of build a system that uses property-based testing to do robust testing of performance properties. I haven't done much with it. But it seems like the kind of thing that should be available, because the thing you want to do when you have performance properties is run the thing a bunch of times, and so that you can smooth out the performance.
Actually, this
And
is a great idea because with when you control the ability to generate your programs, you can even try to generate programs that are starting to tickle your program in a bad way. Like
yeah,
time is a continuous value. You can measure how long some of your tests are taking. And if you can generate a valid program or a valid input that starts to take more and more time, the more you turn up one knob
yeah,
in your property-based tester, well, that sounds very interesting to me.
Some sort
for
of
sure.
Bayesian de-optimizer, which
De-optimizer.
it sort
Yeah.
of runs in the loop, and the feedback it's trying to maximize is like the amount of time your program takes to run.
Yeah.
Yeah.
Interesting. Yeah, I wonder if there are systems out there where people try to do this. My one comment to this, and again, I also don't have any answers to this, but my one comment here is that we build substantial amounts of monitoring infrastructures when
Mhm.
we sort of build these massive systems, right? For example, when GitHub goes down, githubstatus.com will have all of the information about what things are failing and degrading. It's of course delayed, but like there's ways to capture these properties, right? They're kind of out of band. They're not very easily integrated. They're sort of, looking at input like inflows and outflows of real user data. And so I wonder if there are ways people have thought to sort of partition the system such that you can have test inputs from inside your test harness, um, you know, pushing values into a particular part of your system and seeing how its latency behavior changes. Or maybe even send probes, right? Like maybe you could fake a probe which acts as an input from users and see how performance degrades if you do that, or latency degrades.
Yeah. Yeah. So there's a project called Quickstrom, which
Hmm.
uses linear logic to define properties uh, over kind of signals out of the program. And then you run the program and you observe the signals and you write some kind of temporal property to define what that sort of log should look like.
Interesting.
And that's in the context of web apps. I had been working for a little while with an undergrad to see if we could kind of generalize it further. One thing that would be really cool is if you had timing information in that log. And so now you're actually writing a property that says, I better not have larger gaps. I better have a consistent length of gap between times I see this particular message. And you can do kind of timing properties that way.
Right.
I don't know if anyone wants to work on that, let me know. But
Yeah.
yeah, there's like, I think there's probably a lot that could be done there. Yeah.
Yeah, I know that testing distributed systems is notoriously difficult. It's very tough to like
Certainly.
wrap all your code and like test these sorts of properties and timing things.
Yeah.
Yeah, and the tricky thing is the more systems we build, there a lot of them are ending up as distributed systems, or I don't know, I like calling them dislocated systems, where there's like parts of it that are floating in user
Mm,
side, and parts of them are in your control. And so how do you test them? The particular area I work in, sort of hardware design and programming languages, there's a lot of work in random testing, right? Like the hardware folks
yes.
have been doing aggressive random testing for many, many years and have pioneered things like SMT-based verification, model checking, and formal verification. In fact, too, after the Intel floating point processor, Intel was one of the first companies to sort of adopt these verification technologies, right? They actually, I learned recently, they have an interactive theorem prover that uses SAT in the loop to prove properties. I haven't actually validated this claim, but like that sounds really cool and something maybe we should build. But yeah, I think like as we build these systems, one great thing for the kind of work you were thinking about, Harry, is that people do recognize that there is a lot of value in building testing infrastructure, right? We're talking about the social process, and it was kind of a facetious question on my part because like I obviously value stuff like this a lot. I think
Yeah.
like systems like Infer and Coverity and all of these static analyses that have been super successful do this by showing that there are person hours saved by the kinds of bugs they find, right? And they can do it because they sit in the CI system and they can sort of continuously find bugs and tell you that something's wrong. And they can be like, oh, look, this was a memory critical bug. Like if it made into the system, it would be a CV and we would have bad press and we would have to spend a lot of time fixing it. Um, but I think things like formal verification and randomized testing, which are so aggressive that they oftentimes fix a lot of bugs before anything lands, it's hard to see their value by measuring using those effects. So I think, it requires a different kind of model of system design to really
Yeah.
appreciate the value of those things.
Yeah.
Um,
There are
we
plenty of good, if you want case studies, there are plenty of good examples of papers out there of people finding really important bugs with property-based testing. All of the stuff by the folks at Cubic uh, is a lot of fun to read, and John Hughes and Thomas Arts talk a lot about that.
What's
But I
cubic?
agree that in terms of like data that shows that we don't have the same kind of data that shows like, here's the person hours saved and that kind of thing.
What's cubic?
QUVIQ is a Swedish company that does property-based testing consulting.
Oh, interesting. Okay. And they have a bunch of case studies. They have a
Uh,
blog.
they have a blog. They've written papers on this. Yeah, it's
Interesting.
there's cool. They like found bugs in Dropbox and Volvo car software
Yeah.
and all sorts of stuff like that.
Yeah, it's such a good technique. You can start a company and like have other companies pay you to do it. Yep.
Yeah,
right. Yeah, and so going back to this point of like we don't have that much data in the same way. Well, like the data we find is often the absence of bugs. One paper that everyone in the verification community loves to cite is the sort of C-Smith paper, which found an
Right.
absence of bugs in verified C compilers as opposed to all of the existing system infrastructures.
Yeah.
There are reasonable critiques about whether the verified systems implement as many optimizations or are really production grade in the same way that LLVM and GCC are. But still, the fact that you have an end-to-end compiler that is used by people, has no bugs, or at least they weren't able to find any bugs, was really remarkable. And so, yeah, sort of testing for the absence of things is definitely very, very hard, and
Yeah.
maybe sort of a big challenge here. There are a couple of questions from the audience that I just wanted to get to.
Sure.
I think we have a question going back to our conversation about LLMs, and then my comment that you can basically sort of switch them into a feedback mechanism, such that you take your PBT, you connect it to your LLM. Too many acronyms. You take your testing harness and you connect it to your machine learning model, and you provide feedback to the machine learning model using the test that your harness is generating. I think the question is pointing out that we're essentially taking an untrustworthy synthesis system, and I'll ask you to describe what synthesis means, and turning it into a trustworthy verified synthesis system using this feedback mechanism. And so the question goes, do you have thoughts on how this relates or impacts traditional program synthesis? So I guess a couple of high-level things. Let's figure out what this program synthesis thing is.
Sure.
And then we'll talk more about trustworthiness when it comes to program synthesis and what Copilot does.
Yeah. So synthesis is a broad area of computer science, of PL-ish. It kind of goes broader than that. But the idea is, can we automatically generate code? And there are lots of ways that people go about this. So there is example-based synthesis, where you're given input-output examples and you have to synthesize a program that can produce those. There's specification-guided synthesis, where you give a formal specification and you have to synthesize something that obeys that. There's type-directed synthesis, where you have some examples and a type, and you have to give a program that has the appropriate type and does the right thing. But broadly speaking, you're trying to generate some code that will implement a function that you want. You might have seen this actually if you work in Excel and have used flash fill. Flash fill is one of the most used synthesis things out there. And
not anymore, but
well, sure, was correct.
Yeah.
Before Copilot was one of the most used synthesis engines. And right, so Copilot and even ChatGPT, if you're nice enough to it, will generate code for you. And the code that it generates is not related to examples. Sorry, there's some people out in the hall that are being loud, if you can hear them. Not related to examples, nor is it related to a formal specification. Instead, the function it gives you is related to a natural language specification. And that is tricky, because your natural language specification is rarely precise enough to really say what you want. And there's no validation that the thing that you get out actually satisfies that specification at all. And so the question is, right, can property-based testing help here? And I would hope the answer is yes. I'm not quite sure how to do it. But like, property-based testing is a way to, if given code, give back counterexamples, right? You can have a conversation. If you write your property first, you could have a conversation with ChatGPT where you say, okay, give me a function to do this. It says, okay, here, and you run your property-based testing, get a bug, and say, like, okay, that was bad, try again. I have no idea how well that works. But if you get to a point where the property passes, and you've done the appropriate work with the generators ahead of time, you can have some more confidence that the code out is actually what you wanted. Um, so yeah, I think there's opportunities here for sure. Um, yeah, I'm not quite sure how to do it the right way, but I think it could be done for sure.
Yeah, it's this question actually gets to something that's very close to my heart, which is program synthesis. And so I think one of the deep differences in the way where how PL people, programming languages researchers think about synthesis, at least the way I do, and how Copilot works is a real commitment to correctness, right?
Mhm.
So a lot of our techniques in PL are about reasoning and correctness, which is again going back to how this conversation started. You were mentioning that's what really drew you into PL, this like devotion to the truth, as it were, the
Yes.
truth. And so a lot of the synthesis technology that was developed in the PL community is devoted to making sure that the answers you get is correct.
Yeah.
And the sort of weird and unfortunate thing was that it's not really adopted, right? Like it one thing we've realized over the course of doing this for I think about 2 decades now, that specifying programs is just as hard, if not harder, than writing the program, right? And oftentimes the reason formal synthesis, I'm going to call it formal synthesis because it's sort of specific and specifically correct in a way that our technologies might not be, because it requires a specification of what is correct. It's really, really hard to make it adopted, right? There are other technologies also developed in the PL community that use example-based methodologies, which is what Flashfill does, where you have a bunch of input-output examples, and Flashfill tries to generalize the output for you, right? There are other technologies which are enumerative and so on and so forth, but again, they're all sort of trying to hold on to this correctness. And one thing I've noticed with sort of the adoption of Copilot and related technologies is that somehow people don't care about correctness, right? What they care about is maybe a step forward, right? If you're stuck or if you're new to a code base, a step forward feels better than a specification, right? Like if and here's an example, right? If you take me and today drop me into the code base of the Rust compiler or memcached, I don't know what to do, right? Um, but if I say, here's my comment, here's the thing I want to do, and it generates a bunch of text for me, even if it's garbage, as long as it gets the method names right, and I can jump to those relevant methods and look at them, I can build context that is more specific than what I would have to do normally, which is like, okay, let's look at the middle part of the Rust optimization pipeline. Let's find out what the mir colon colon uh, type enum means, right? As opposed to just saying get inferred type or something, which is a method defined on the context, let's say, right? This is getting too
Yeah.
specific. But you get the point, right? Like one of the remarkable things about these technologies is that they can often act as your own personal context sensitive Stack Overflow. That's how I
Yeah.
describe it to people, right? Like
Yeah.
it's like you shouldn't use it for correctness. You shouldn't use it for like generic code. You should use it as Stack Overflow that is aware of what you are trying to do and is much faster at responding to your queries. Um, and so, yeah, they're somehow very different technologies, right? Like if you take this as Stack Overflow and a formal spec, well, yes, of course they can interact with each other. The formal spec tells you why the Stack Overflow is wrong. And if they get a good mechanism of building sort of that feedback loop, they could do something really, really cool and remarkable.
Yeah.
But there's like a piece of my heart that just dies when like, LLM and synthesis is the dominant way people will think about program synthesis.
Yeah.
It's a
Yeah. I mean, there's the kind of unavoidable truth that like no like code is very rarely thrown away, right? You say you're going to do the gross quick version and then throw it away and do the real version, but it doesn't often happen. And so I think that's the trick is to catch the user right before they start using their Stack Overflow generated code to do the real thing, and you say like, hang on, let's think about a spec here because this doesn't do what you think it does, or
But
at
it's
least it might
very
not.
close, right? The key is
Right,
that it
right,
like out of the
Yeah.
space of all programs. Copilot's very good at like narrowing down on like you might want to use these functions in this
Yeah,
order.
yeah,
Right.
yeah,
But yeah, this is sort of this is why I say that. I think you said the sentence while we were talking about this, Harry, which is like, what happens when we live in a world where most of the code we're testing is not the code we wrote, right?
right.
This is something that used to happen where we had test engineers separate from code engineers, and places like Google don't do this anymore. You write your own tests, but like with LLMs generating code for us and them getting better, we will all become test engineers. And so there's
Yeah,
a question of like, how good are you understanding code, right? And so
yeah,
here's my pitch for all of these like interview companies, right? There's like a bunch of places that will interview you and then like instead
yeah,
of making me write code, give me a piece of code and ask me to tell you why it's wrong. I think
yeah,
that often acts as a demonstration of a much more competent sort of a programmer than someone who can write code, right? Because it's sort of you really need to understand what the code is doing and think about all of the edge cases, which is, I would argue, a much more critical skill in programming potentially than writing the code itself. Um, but yeah, it's a brave new world and it's scary, but I think there's opportunities here, of course. The one thing I would point to people if they haven't read it, there's this great blog post. It's called The Bitter Lesson, and it's about the march of machine learning and how like people often thought that domain insight would often matter when you're doing such, for example, natural language processing or vision processing and stuff like that. And somehow the thing that has mattered are technologies that can scale with compute. That's what has mattered more than domain insights, right? And so that is one thing that is missing in our understanding of formal logic, like program synthesis. SMT technologies, which is what often do the formal
yeah,
synthesis, they do scale. They don't scale very well in the way matrix multiply has.
right.
But the fact that matrix multiply scales well means that we can build all of these technologies, and they'll be slow like 20 years ago, and now they are just changing the world everywhere because they could harness into that forward march of computing itself. Um, yeah, that might be a good place to end this actually, even though I ended on the
Yeah,
bitter.
we definitely went down the Copilot like rabbit hole. Every stream podcast, it's inevitable, but we did it. So
No, but yeah, I think sort of it comes back to specification, right? Like I think a big theme here was like what is specification and why it matters for testing and everything
Yeah.
else.
no, it
Uh,
definitely like tied in well to like as a contrast, like a compare and contrast.
Mhm.
okay. So to wrap up, I have two prompts for you. One is if you had to give like a two-sentence piece of advice or summary to programmers and researchers out there to use your technology or to think about testing or philosophy or something that you think is really cool and concise, what is that two line paragraph or something? And then the second prompt is maybe what are three things that you were interested in reading or watching in the last couple of weeks? What have been pieces of writing and audio or visual content that you have enjoyed?
So my summary advice is that if you're a programmer or a researcher or anyone who writes code, um, learn what property-based testing is and how to do it in your language because it's available. Because I'm confident that there will be some places where you will get a ton of benefit from it. And I'm not saying you should use it for everything. I'm not saying that it's the end all be all of testing, but I think there are definitely places where it will improve the quality of your software if you know about it and know that it's available to you as a tool. Um, my thing. So I think I've given folks plenty of things to read. I like dropped a lot of things to read. The one thing I'll add, which is just a thing that has been on in the back of my mind lately, is so I do a bunch of work in PL mostly, but I like to dabble in human computer interaction because I think there's a lot of benefit to bringing those ideas in. It gives us grounding for our work, and it helps us to stay on the right path of actually benefiting users. And so I'm going to recommend a paper from 2007 called Evaluating User Interface Systems Research. And Dan Olson is the name. And the reason it's not about PL, it's about how to evaluate work that folks were doing with UI toolkits, like kind of tools for building user interfaces. But it turns out that that programming languages are tools for building programs, which are kind of user interfaces, and so like there's a lot of cool connections, and I think I may make a YouTube video about this at some point. But
Oh, great.
it's a cool paper with a bunch of cool nuggets, and I think it may give you some ideas for ways to motivate the work that you're doing.
Awesome. Well, thank you, Harry. This was, as always, a great conversation. We learned a lot. Um, for our audience, we are off next weekend, but the weekend after that, we're going to have Oliver.
We are going to have another Sam. We only interview Sams and Harrys on this show, and Sam will be telling us all about computer hardware, floating point, and how these relate to programming languages, and what techniques we can borrow from programming languages to make hardware faster and more correct. So one of our big goals on this stream is to bring in people outside of programming languages. And of course, because Rachin and I are both grad students in this area of research, we love to connect it to programming languages. So stay tuned. We're going to be every other week from now on. So we'll see you all in 2 weeks. And we also wanted to say, if you want to be on the show, or you know someone who you think would be great on our stream, or you know people who would write great questions for the stream, you should invite them. Do you have anything to add, Richard?
No, I think you hit it on the head. I think if you know someone who would be interested in coming, please drop us a line. Our emails can be found on our web pages, respectively. My web page is rachit.pl. It's very easy to remember. And Oliver is oflat.com. I want to say it.
Yeah, oflat.com. And remember, 2 weeks we'll have Sam Coward on the show. Very excited for that.
Awesome. Thanks again, Harry.
Thank you. It was great.
Yeah, we'll see you all 2 weeks from now. Bye-bye.
Bye, everyone. Thanks for coming.
Thanks, everyone.